In Chapter 2, we're going to look at describing distributions with numbers. One important thing to remember in this particular chapter is we are always going to be working with quantitative random variables, quantitative data, and of course another name for quantitative is numerical data. We will not be working with categorical data in this particular chapter because we have other ways to describe distributions that have categorical data instead of quantitative data. We're going to be looking at measures of central, specifically the mean and the median. We will also be mentioning the mode. Measures of spread that we're going to be looking at are quartiles and the standard deviation. And along with the standard deviation, we usually find the variance first, so we'll be bringing up variance as well. We'll be looking at the 5-number summary, and then a graph of the 5-number summary is called a box plot. So a box plot is a specific type of graph. And with the box plot, we find out stuff about interquartile ranges, IQR, and outliers. And instead of just saying outliers are data points that don't fit the general trend of the data, we now will have a mathematical way to describe an outlier, what to do with outliers, and then all these summary statistics that we have, the mean, the median, the quartiles, standard deviations, how do we choose which of those is best to use? And at the very end, we'll look at how we organize a statistical problem. When we get started working here, the thing to remember is not all data is the same. For instance, if I were to go around the room and ask each one of you the number of credit hours you're taking this semester, you're not all going to reply with the same value. So there's variability that's inherent in data. And because of this variability, we like to be able to talk about one single measure that will describe the entire data set. To get started with this discussion, let's go ahead and start by looking at measures of center. Now, another name for measures of center are kind of like measures of central tendency or measures of location. They give us an idea about where a data set is typically. Not every single data point, but one number or one spot that best represents the entire data set. So the first one we're going to look at is the mean or the arithmetic average. Now, we all know how to calculate the mean. We've probably seen it done several times before, but let's go ahead and look at the shorthand notation here. This formula means x bar. X bar, this symbol is used to represent a sample mean. Now remember, we have samples and populations. X bar represents a sample mean. And as a side note, the Greek letter mu, this is not just a u, it's a mu, Greek letter mu, represents the population mean. So if you see a Greek letter, it usually represents a value from the population. So what we're doing here is we're trying to get x bar as a good estimate of what the true population mean is. And so x bar is called a statistic. A statistic is a numerical value based on a sample. Now, under here, where we have this Greek letter mu, this is called a parameter. A parameter, again, is based on a population. It's a numerical value that is based on a sample. Now, these are really good test and quiz type questions. Or, I'm sorry, not sample. Population, we just did sample up above, so based on a population. Now there's a really good easy way to remember this with a mnemonic. Statistic starts with S, so does sample. So a statistic describes a sample. A parameter starts with P, so does population. A parameter describes a population. So the whole idea here with what we're working with is we want to use a statistic to estimate a parameter. Now, there's a lot of different statistics and there's a lot of different parameters. What we're starting with is x bar, which is the sample mean. So again, this is an important idea. Statistics estimate parameters. We can't take an entire census of a population, so we take a sample, and based on what we find in that sample, we use that to estimate the population over here. So back to what this notation looks like. X bar represents sample mean, x1 plus x2, etc., all the way up to x sub n. And remember, lowercase n represents sample size. This lowercase n is the same, represents sample size. This means to take all of our observations and add them up and then divide by the total number of observations. Now over here I have a shorthand notation on how we write that. This is the Greek letter sigma, and it means to sum or to add up. So this means to add up your observations from the first to the last and multiply by 1 over n, which is the same as dividing by n. So these are the formulas that we have for calculating the sample mean. Now obviously Excel does this very well, so does Minitab, but you're definitely going to be able to want to do this on a calculator as well. So there's a couple different ways to do this. Sometimes you can enter data into your calculator and then ask for it to output summary statistics, or you can just physically go through and add up the values and divide by n. And if you have questions about your calculator, make sure you bring them so we can have a look. Let's go ahead and look at an example of how you can calculate the mean or the arithmetic average of a data set. So for this example, we are going to be looking at IQ scores. So suppose, this is an S with a P hanging from it, it's shorthand for suppose, we have IQ scores that we're going to be looking at. And the IQ scores that we're going to be looking at are 145, 139, etc. So after we have these recorded, first of all, I would note that we have n equal, let's go ahead and count these, 1, 2, 3, 4, 5, 10. We have n equal 10. 10 is our sample size. Now to find x bar, we need to take all of our observations and add them up and divide by our sample size. So we already have part of this. We know our sample size is 10, and then here in the numerator we need to add these up. So go ahead and pause and take a second to add these up. And if you add those up, you should get 1,229 divided by 10 is 122.9. So this is x bar. This is your average IQ score based on this particular data set. Now usually we have some sort of units that are associated with this, but IQ scores you just state as they are. They're not feet, they're not inches, they're not pounds. It's just a score. So my average score here is 122.9. So mean is one measure of central tendency that's very commonly used. Now the next one we're going to look at is called the median. Now the median is based on not looking at every single particular value. So if we look here at x bar, we used every single one of these numbers when we calculated x bar or the sample mean. Now down here, let's go ahead and talk about the measure of center or the median. Now for the measure of center, the median is the midpoint of an ordered distribution, and this word ordered is so important. If your distribution is not ordered from smallest to largest, finding the median is very difficult. And of course, if you have software to do it for you, it orders it internally and you don't see that process. But when we find the median by hand, it's really important that we order it. So the median is the midpoint or the middle of an ordered distribution. It's a number such that half of the observations are above that value and half are below that. So half are smaller and half are larger. It's also known as the 50th percentile. And this is a percent sign with an ILE, percentile, but we'll learn about 50th percentiles in a little bit. And its symbol, this book uses a cap M for median. Other books use X tilde to represent median. So you'll see these interchangeably during your reading of the textbook, the reading of other books, the reading of journal articles, and also during our lectures. So you'll see cap M, but probably more commonly this X tilde is known as well. So when we're finding a median, there's basically one thing that we need to look for first. Is the data ordered? And then after we've assured ourselves that the data is ordered, we have to determine, do I have an even or an odd number of data points? So again, first thing we should do is sort the observations from smallest to largest, and then we note how many observations we have. And again, lowercase n is our sample size. Now the location of the median is going to be our sample size plus 1 divided by 2. It's going to be that number observation in the sorted list. So let's go ahead and look at two options here. Let's suppose n equal 12. I have 12 observations. This implies the median, X tilde and M are the same as the median, is we take 12 plus 1 over 2, and again that formula comes from right here. So this is 13 over 2. This is the 6.5 observation. Well, there's not a 6.5, so what I have to end up doing here is average the 6th and 7th observations. So when I have an even number of data points, I have to end up averaging the middle two. Let's go ahead and look at another case where we have, let's say, 15 data points. X tilde is the 15 plus 1 over 2, and again, this is coming from right here. And I wouldn't spend a lot of time memorizing this formula because it does make intuitive sense to just find the middle of something. So here we have 16 over 2, or 8, so this would be the 8th observation in the data set. I wouldn't have to average anything. So that's the next thing we need to look for is, do I have an even or do I have an odd number of data points? Let's go ahead and look at an example on how we could calculate both. So for our first example, let's go ahead and look at where we have an odd number of data points. So here this example is for odd number of data points. Now we have to be kind of careful of what we're looking at here so we don't get confused. First of all, this data is sorted in order from smallest to largest, and so this is our data points right here, the 0.6, etc., all the way up to 6.1. So this is ordered. Now what's happening here is this gray column has the ranks. Okay, so these are ranks, meaning my first observation, my second observation, etc. So again, this is our original data, and the gray column is the ranks. Now in this particular case, we see that there's 25 data points, n equal 25, our sample size is 25. So in order to determine where the median is, we take 25 plus 1 is 26. 26 divided by 2 is 13th. So I go and I find the 13th observation. Now the 13th observation from the top here, or if I wanted to order this way too, I could see that this would be the 13th from the bottom as well. So the 13th observation is 3.4, so therefore the median equals 3.4, or if we're using symbols here, x tilde equal 3.4, or that cap m equal 3.4, and again you'll see those interchangeably. Let's go ahead and look at an example where we have an even number of data points. So again, in this data set we have an even sample size, we have an even number of data points. Same as before, in this particular case this column in the gray is the rank, meaning the first, second, third, fourth, fifth observation. And this is our actual data. And this data is ordered as well. Now in this case, my sample size is 24. Notice I don't have this 25th observation here. So in this case, my sample size is 24. So now how I calculate my median, I'll end up averaging two middle values. So again, I'll take my sample size of 24. 24 plus 1 is 25 divided by 2 is 12.5. So that means I'm going to average the 12th and the 13th observation. So I come down here through my rankings and I find my 12th and 13th, and so I want to find the midpoint between 3.3 and 3.4, so I add them together and divide by 2, and what we get here is 3.35. That's my value for the median. So I get cap m equals 3.35, or of course x tilde equals 3.35. Different symbols that represent the same thing, which is the median. So again, it's pretty intuitive. The important thing to remember is order them first before you find the median. Because if you don't order them first, just that random selection that you have there, you may or may not get the median. So ordering, remembering to ordering is so important. So now that we have these two measures of central tendency, we can kind of mention that third one that I said wasn't as important, but we would bring it up. And it's called the mode. The mode is the most frequently occurring data point. Now the bad thing about the mode is it only takes into account what happens the most often. It doesn't take into account other data points. So for instance, up here, when we were calculating the median, I really only used these middle values, but I did use the ranking of all the other data points. Now remember, in the mean, I used every single value in the calculation. Here, I'm just using the ordering of the values. Well, in this particular data set up here, the most frequently occurring value, it looks like there's a repeat right here at 2.3. So for the mode in this particular data set, we'd have 2.3. And we don't have a symbol to represent it. So for this data set, the mode would be 2.3. We don't use a symbol to represent it, we just usually state it. But again, we don't use it as a measure of central tendency in and of itself very often because it doesn't take into account any other data points. It's just taking into account the most frequent values. So that's the mode. Now the next question is, how do we determine which of these measures of central tendency to use? Let's go ahead and look at some data sets to try and determine which measure of central tendency we should use. So we are basically comparing the mean and median. So let's go ahead and look at this first data set. So data set 1, let's suppose we have 5 observations. We have the observations 1, 2, 3, 4, and 5. Those are our data set points. Well, it's pretty easy to talk about x bar and x tilde here. Let's do x tilde first. X tilde is the median, don't forget. This is ordered, so x tilde would be the middle value. Now here, x bar, remember, is the sum of the x's over n. In this case, I have a sample of 5 data points, and if I added up these 5 data points, I'd have 9, 10, 11, 12, 15, and 15 divided by 5 is 3. So to summarize, for this particular data set, I have x bar equal 3 and x tilde equal 3. Now there's an important characteristics here. This is called a symmetric data set because if I chose this middle value, each value to the right and to the left of it is evenly spaced. So this is a symmetric data set, and because it's a symmetric data set, the mean and the median will be identical as we have here. Let's go ahead and look at another data set. Now we're going to have virtually the same data set here, but let's go ahead and change this 5 to, let's say, 100. Well, clearly 100 seems to be an outlier here. So let's analyze the effect that this outlier will have on our statistics. So we'll calculate x bar and x tilde again. X tilde again is the easy one. These are in order from smallest to largest, so x tilde will be this middle value, which is 3. Notice it didn't change. Now x bar, I would add up my values and then divide by my total number of values. I still have 5 values, but when I add these up now, 7, 8, 9, 10, I get 110 over 5. Now when you figure out what 110 over 5 is, we'll see that, you know what, this doesn't really seem to represent the data. You'll get 22 here. So now my summary values are x bar equal 22 and x tilde, the median, equals 3. So what ended up happening here is this outlier severely influenced the sample mean, but it didn't affect the median at all. So that's kind of our takeaway point here. The mean, x bar, is influenced by outliers, because clearly 100 is an outlier here. The median, and again we're using x tilde or that capital M for the median, is not influenced by outliers. Now we'll see a lot of terminology to represent this, but basically the mean is being, what we say is it's not robust. It's influenced by, it's affected by. The median is not influenced, so we say that it is robust. And again, that's some common terminology that you'll see when you're reading through different articles and texts comparing these types of things. So again, outlier influences the mean, outliers don't influence the median. And so that's one way that we can talk about comparing the mean and the median. There's some other terminology that you might see as well. We could say the mean is influenced by outliers, the mean is not robust to outliers. We can also say that the mean is not resistant to outliers. And I'm putting all these different ways that you'll see this red just so it's familiar to you when you come across it. The median is resistant to outliers. So again, these are just different ways that you'll see the same thing said over and over again. Now when we're talking about these mean and median comparisons, we usually like to talk about these in terms of a graph. So let's go ahead and look at some graphs. Now the graphs that we're going to look at are actually quite familiar. We've talked about them several times. In this particular distribution, we recognize this as being a symmetric distribution. For a symmetric distribution, the mean and the median are equal. So for a symmetric distribution, this midpoint, this high point right here, x bar and x tilde are the same. The mean and the median are the same. Now over here for a left skew distribution, what ends up happening is these outliers over here end up pulling the median and the mean apart, and the mean goes toward the outliers. So the mean is always skewed in the direction of the tail. Now over here for the right skew distribution, the same thing happens. For a right skew distribution, the mean is pulled toward the tail. So again, for a left skew distribution, x bar is always in the direction of the tail, so x bar is always less than x tilde. And for a right skew distribution, the mean is always in the direction of the tail, and x bar is greater than x tilde. The mean is greater than the median. Now these graphs are kind of some generic graphs just talking about general shapes of distributions, but next we want to look at some specific graphs and how we can analyze those graphs based on their shape, their mean, and their median. So first of all, what we have here are two different distributions. We have the distribution of years until death and after diagnosis with some disease X, and here we have years until death after diagnosis with multiple myeloma. So when we're looking at these for disease X, this is kind of our unknown. Notice that x bar, which is our sample mean, and m, which is our sample median. And again, please keep in mind that sometimes you'll see this denoted as x tilde, same as the one down here. The mean and median are the same, and my picture looks to be very symmetric. So what we have here is a symmetric distribution. And because it's symmetric, this implies that x bar and x tilde, or the cap m, are the same. Now if we look down here, we can see that this is very much a right skew distribution. So this is a right skew distribution, and for a right skew distribution, I would expect to see that the mean would be pulled toward this outlier and this tail over here. So what I would expect is the mean to be larger than the median. So let's see if that's true for this case. So if we were to graph these values, x bar would be somewhere over here at, let's say, 3.4 about. So here's x bar, and the median was over here at 2.5, which is x tilde, or the cap m. So we can see that the mean is larger than the median. So again, the mean is pulled toward the skew and the outliers, and the skew is in the direction of the tail. And over here, the mean and the median are the same, right about here at 3.4. So again, x bar and x tilde are the same here. So for both diseases, X and the multiple myeloma, you have on average of 3.4 years to live after you've been diagnosed. However, of the 25 people with disease X, and we can tell that there's 25 if we were to add up these bars, because here's one person, here's 4, so 1 plus 4 is 5, and you could go through and add these up. So again, the 25 people with this top disease, only one died in the first year after diagnosis. However, in the first year of diagnosis with multiple myeloma, 7 passed away. So we can see that the average survival of 3.4 years that has been recorded, the X bar for each of these, notice, is 3.4 years, doesn't provide all the information we need. Something more like the median and the shape of this distribution provides a lot more information. So the takeaway here is to really understand a data set, you have to plot the data and look at the distribution and look for things like the overall shape, the skewness, symmetry, any presence of outliers. And you should also understand the effect that these different shapes of the distribution have on the descriptors like the mean and the median. So again, not only just look at the picture of the graph, but also look at these numerical summaries that describe the distribution and the numbers. Well, that's about it for measures of location and measures of central tendency. The next thing we're going to do is look at measures of spread, and the first measure of spread that we're going to look at is quartiles. First of all, measures of spread or quartiles are based on the median. The standard deviation that we'll talk about here in a little bit is based on the mean. So quartiles, box plots, interquartile ranges, all this topic covers is based off of the median. So that's something very important to remember. Let's go ahead and look at a data set, and then we can look to see how we go through and calculate quartiles. Because quartiles are based on the median, you must remember to order the data. So before we even get started to find quartiles, order the data. Now this data set should look familiar because we have used it before. So what we have here is the ranking of each data point. Is it the lowest or is it the highest? And then we actually have the actual data. Now in this particular case I have a sample size of 25. Now the first thing we do to find quartiles, and as the name suggests, quartiles takes the data and it splits it into quarters or 4 equal parts. So the first thing we do when we're trying to find quartiles is you find the median. Now because I have 25 data points, 25 plus 1 is 26 over 2 is the 13th data point. So this is my median right here. Then what I do is I treat each of these as an upper and a lower data set. So for this upper data set, I can see here, and again I'm ignoring the median because I've already used it. Okay, so for this upper data set I can see I have 12 data points. Well, that's an even number of data points, so 12 plus 1 is 13. 13 over 2 is 6.5, so I'll average these two between 2.1 and 2.3, and I get 2.2 here, and that's called Q1, which represents my first quartile. And it's also known as the 25th percentile. So these are all names that are meaning the same thing. So this is the 25th percentile, and again the percent sign with an ILE is the 25th percentile, and I get 2.2 for that. Now here for the median, remember we use X tilde or the capital M. This is also known as the 50th percentile. Again, the percent sign with the ILE, and in this case that is equal to 3.4. So that's the 50th percentile. Then I do the same thing up here for this data set. I'm going to have 12 data points, average the middle 2 points. So this one is called Q3. And if you notice, I have quarters. I have 1 quarter, 2, 3, 4 quarters of my data set. So this one is Q3. It's called the 75th percentile. And we've all worked with percentiles to know that with a percentile, what they're referring to is how you are compared to all the other values in a particular data set. So if you're at the 70th percentile, 70% of the data values are lower than you and 30% are higher. In this case, the average between 4.2 and 4.5 is 4.35. So that would be my 75th percentile. So to summarize how we found these, the first quartile, which is Q1 or the 25th percentile, is basically the median of the lower half of the data set. The third quartile, Q3 or 75th percentile, is the median of the upper half of the data set. And this is how we go through and we find our quartiles. Now this was when we had an odd number of data points, because here our sample size is 25. So our next example, I would like to look at finding the quartiles based on the median for an even number of data points. So for this example, this is again familiar. We're looking at the skin healing rates from 18 newts measured in micrometers per hour. So in this particular case, 18 is our sample size, n equal 18, and this is an even data set, so this is going to be a little bit different. So here's the raw data, and if you notice, it's not in order from smallest to the largest, so the first thing that we should do is order the data. After we order the data, and again from smallest to largest, the first thing we need to do is find the median. So the first thing we do is order the data. The second thing we do is we find the median, or the 50th percentile. And then, it doesn't matter if we do step 3 and 4 here in either order, but we find Q1 and Q3. So you could find Q3 first, it doesn't matter. So again, I have 18 data points here. Now because I have 18 data points, I know I'm going to have to end up averaging the two middle values. So when we work through here, I take 18 plus 1 is 19, 19 over 2 is 9.5. So we need to basically average the 9th and the 10th values. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the true median is actually right in between here. And the average of 26 and 27 is 26.5. So my median is 26.5. Now what I need to do is I need to find the middle of the lower half and the middle of the upper half. Now this is where things change a little bit. Notice up here, when I had an odd number of data points, I actually physically used the median, and once I used it, I no longer included it. Now down here in this data set, I didn't actually take a number out of the data set to call the median. So now my upper half of my data set includes 11 through 26, and the lower half includes 11 through 26, and the upper half includes 27 to 40. So now I have an odd number of data points. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the median of the lower half will be the 5th data point in from either side. So this is Q1, or my 25th percentile. Same as up above here, I go in 5 from either side, and I get Q3 to be my upper quartile, my 75th percentile. So to summarize here, I have Q1 equal 22. I have Q2, which is the median. You'll also represent it as cap M, is 26.5. And I have Q3, which is 33. Now this kind of gives me an idea about how spread out the data is. Pretty soon we're going to use all these summary values when we start taking these and making a pictorial distribution or a pictorial representation of the data called the box plot. But for now I want to skip to the other measure of spread called the standard deviation. So when we talk about the standard deviation, we need to realize, of course, that we're not talking about the median anymore as the basis for this measure of spread. Here we're talking about the mean being the basis for this spread. So the standard deviation is used to describe the amount of variation there is about the mean. Up here, the quartiles, we're talking about the amount of spread there was about the median. So make sure that you understand the difference between those. Now, there's a lot of interesting calculations that go into calculating the standard deviation. I'll give you the formulas, but basically, you really want to be sure that you know how to use your calculators on a test or a quiz to calculate the standard deviation. And I can show you how to do that, or you can look at your owner's manual on your calculator to figure that out. But make sure you let me know if there's any troubles right away in figuring that, because we will have a test or quiz coming up very soon. Now, to get the standard deviation of sample data, I basically apply a formula. Now, the formulas get pretty involved, so again, that's why I highly recommend that you learn how to use your calculator. Minitab will calculate these for you as well, but on a test or a quiz, you won't have Minitab, so you'll need a calculator. So again, the formula is here. Now, before I calculate the standard deviation, I find a measure called the variance, and it's represented by S squared. So S squared is the sample variance. And again, it's important that you know what these symbols mean. Now, all of our units up above for measures of measure of central tendency or location were standard units. So minutes, hours, seconds, feet, yards. Here, my units for variance are squared, and it's easy to remember that because it's S squared. And then to find the standard deviation, I just take the square root of the variance. So S stands for sample standard deviation. And now our units are back where we want them. They're just standard units. Now, sigma squared, Greek letter, is the population standard deviation, population variance. And sigma is the population standard deviation. And the units are the same as they are up above. So as before, we use a statistic to estimate a parameter. So up here, S squared and S are statistics. Down here, sigma and sigma squared and sigma are parameters. So again, statistics estimate parameters. Well, this is the formula that we use for the variance, and then you take the square root of the variance to get the standard deviation. And you can see here that it's a pretty involved formula, but basically what we have here is we're looking at the average of the squared deviations. Now, if we were to ignore this squared right here, the sum of each observation subtract the mean would give us 0. We square it, so we're looking at positive values, so they won't sum to 0, and then I'm dividing by the sample size minus 1. So this is the sum or the average of the squared deviations. Now again, learn to use your calculator here. Now, because each of you probably has a slightly different calculator, okay, I'll leave that up to you to try and figure out, and if you have questions, please let me know. I'd be happy to look at your calculator with you. If you don't have your owner's manual anymore, you can certainly go online and Google your calculator model number, like TI-89 or Casio 13X or something, and you'll find your owner's manual online, and it will take you through step by step how to find this. If you have troubles, please let me know. I'm happy to help you figure that out. Now we're going to do one of these by hand, and we might actually do another one by hand on a test or a quiz. But to get us started here, let's just go ahead and look at an example. And we're going to need plenty of space, so I'm going to move down here a little bit. So for this example, we're looking at a person's metabolic rate. And the person's metabolic rate is the rate at which the body consumes energy. And what we're going to do is we're going to look at a data set. And the data set is of a random sample of 7 men. And we want to find the mean and the standard deviation of these metabolic rates for these 7 men. So let's go ahead and first of all look at the raw data. So to get started, if you notice here, I have 1, 2, 3, 4, 5, 6, 7. So this is my sample of size 7. So I know right away that n equals 7. My sample size is 7. And these are my observations. So for the first man, his metabolic rate was 1,792, and these are kilocalories per 24 hours. The second person had a metabolic rate of 1,666. So these are my observations. The first thing that you need to do to apply the formula is to actually go through and calculate the mean. And the way we're going to go through and calculate the mean is to take the sum of the x's over n. So the first thing we'll do is we'll calculate the mean, x bar. X bar is the sum of the x's over n. Well, we know we have 7 men because we counted them up here. But if we look at the total here, we can also try and come up with this numerator. So let's go ahead and look at totaling this value. And this value would be called the sum of the x's. So if you add all these up, you would get 11,200. And that would be your numerator here. 11,200. And then to find the average, you take 11,200 divided by 7, and I would get 1,600. This is the average metabolic rate. Now remember, the formula that I'm trying to use here is s squared, and again, I'm starting with s squared, and we'll take the square root of it eventually, but I'm starting with s squared equals the sum of each observation minus the mean quantity squared over n minus 1. That's what we're looking at. So here's this column is my observations. Next, I want a column that takes each observation and subtracts the mean. So this next part of the chart takes 1,792 and subtracts 1,600. Then I take each observation and subtract the mean. And when I add these up, again, sigma is sum, I'll always get 0. Every single time. It's kind of a nice little checkpoint. It's not very informative, however. So our next step, we want to take the deviations, like up here we have in our formula in the right-hand corner, and we want to square those deviations. So let's see the effect of that. So on our next screen here, what we did is we took the 192 and we squared it, and then we have 36,864. And I go through and I do that with each observation. Now notice when you square a negative number, you get a positive value back because a negative times a negative is a positive. And then I add all of these up. Now this is basically my numerator. This is equal to the sum of the x minus x bar quantity squared in this formula up here. Now to go ahead and calculate s squared, I just take this numerator, 214,870, and I divide it by my sample size minus 1. Now my sample size minus 1, they discuss that a little bit in the text, so hopefully you read through that section as well. That's called degrees of freedom, and it's abbreviated DF a lot of times. So when I have degrees of freedom, there's kind of a whole other definition behind that that we'll talk about when we get to the t-distribution later on in the book. But for now, we'll just kind of take it as face value. And I get s squared equals 214,870 divided by 6. And so I get s squared equals 35,811.7. Now don't round here, leave this in your calculator. To find s, I take the square root of s squared, so I would take the square root of 35,811.7, and I get s, the standard deviation, is about equal to, it's not exactly equal to, so I should probably use about signs here, 189.2. So the average standard deviation of the metabolic rates of this sample of 7 min is about 189.2 kilocalories per 24 hours. And again, you've got to learn to use your calculators to do this. Minitab will do it as well. And if you check out the technology manuals on Stats Portal, they go through step by step and show you exactly how to do that in Minitab or in Excel. The next thing we're going to go over is something called the 5-number summary. Now we're kind of jumping around a little bit here, but we've gone over the 2 measures of location, mean and median. We've gone over 2 measures of spread, quartiles and the standard deviation, and now we're going to look at how we can view those graphically. So we're going to start with talking about the median and the spread, the quartiles, in a graphical display called the box plot. Now here's kind of the whole shooting match in one shot, but I'll go through and explain everything here step by step. Now this is data that we've already looked at. Now first of all, I would like you to note, we usually looked at the data from 1 to 25, now I'm looking at it from 25 to 1, and the only reason I'm doing that is I'm looking at a scale here, and if you think about a thermometer, temperatures go from low to high, and so that's kind of the same concept here because I'm looking at a number line moving up vertically, so it makes sense my numbers go from lower to higher. So we've already looked at this. We already know how to find the median, and again, another name for the median is Q1 or X tilde. Another name for Q3 is the 25th percentile. I'm sorry, Q3 is the 75th percentile. Q1 is the 25th percentile. Okay, and then up here I have this new data point that I have never found before, and it's called the maximum value. It means the largest value in a data set. And here I have the minimum value. So this is what's called my 5-number summary. So 5-number summary, and we haven't talked about outliers yet, but for now the 5-number summary is basically in order from smallest to largest or largest to smallest, it doesn't really matter. The max, Q3, Q2, Q1, and the minimum value. And then what I do is I take this and scale this and I graph each one. Now what we do for the maximum is we usually put a point here, and this graph has a little bit of a line so it's easier to see, but there's usually at the very least a point to represent this for the max and the min. So for the maximum point and the minimum point, I note those on the graph. Now the maximum point was 6.1, so you can see my scale of 6.1 here. Now again, this used a little bit of a bar, and you'll see that as well. Now for the median, Q1 and Q3, you use lines as such. And then what you do for Q1, Q2, and Q3, you connect those lines in a box. And so a lot of times that's why this is called a box plot. And then I draw out from the box to the max and the min these straight lines, and sometimes those are called whiskers. So sometimes you'll see this called a box and whisker plot. And so basically a box plot or a box and whisker plot is the graphical display of a 5-number summary. So again, box plot or a box and whisker plot is the graphical display of a 5-number summary. Now a lot of times we like to use comparative box plots. Well, we'll compare one group. We'll compare disease X to disease Y, and then we'll look at the shapes of the distribution side by side. And those are called back-to-back box plots or comparative box plots when we're working with those. Now like I said, one thing we really haven't talked about here are outliers. So when we look at this data set, it doesn't really look like 0.6 is that far from the bulk of the data. It's only 0.6 units from 1.2, and 6.1 appears only 0.5 units from the point below it. So I don't see a huge difference here. One thing I would like to talk about with this particular box plot is the shape of the box plot. So first of all, it looks like to me that this box in the middle and this line is perfectly centered. That's indicative of a symmetric distribution. So the box part says symmetric. Now here, these distances appear to be very similar. So the box part says symmetric, and then the whisker part says symmetric. Now sometimes the box and whisker parts will agree and sometimes they'll disagree, but when they agree, we can say that the overall shape of the distribution is symmetric. We can also look at this and it doesn't appear there's any outliers because I don't have some extreme point, let's say coming clear up here, that would be a lot different from the data set. So that's how we can talk about box and whisker plots. Now what I want to talk about next are outliers. And what do we do with outliers, and how do we treat them, and how do we find them and calculate them? Actually, before we talk about outliers, I got a little ahead of myself. We'll talk about outliers in the context of this graph, but first of all I want to look at that back-to-back or comparative box plots. So like I said, a lot of times we like to compare box plots side by side. So remember, we've already looked at this data set. This was for disease X and this was for multiple myeloma. So here, in this particular case, this was the box plot taken from this distribution that we have already looked at in the previous, further up when we calculated the mean and the median. And then here is the box plot here for the multiple myeloma. So here we can see that this distribution was clearly right skewed. This one was clearly symmetric. And we can see how symmetric these points are here as well to represent that. Now here, in this particular box plot, we can talk about the shape of this distribution. Now this appears to be an outlier. See how extreme it is from the bulk of the data. So I think this is I'm pretty confident in saying this is an outlier, but we'll look at it a little bit more closely when we have a definitive explanation to what an outlier is, mathematically speaking. And then from here we can start talking about the shape of this distribution. Now if we were to take this box and just talk about the box, if you notice there's more area or distance above or to the right if you look at it sideways here. So this is indicating that I have right skewed data, and we can clearly see, and again we're talking about this from the perspective of laying it on its side or looking at it from its side, with this extreme data point that I have a right skewed distribution. So the histogram represents that, and so does the box plot. So again, this long piece right here, because I'm so far from the bulk of the data above, would be indicative of a right skewed distribution, and so would this center mark with the median in this box. So this would look, if I laid this down on its side, it would look similar to a graph like this. Not exactly, but similar. Now a left skewed distribution would have the bulk of the data over here. If you notice here, the bulk of the data, the 50th percentile, is all skewed to the left. So you should be able to look at a box plot and talk about the shape of the distribution. Now you might say, well, what about the case where I have the line over here, and then I have this huge skew over here and barely anything over here? Well, that's always, there's always those cases that it's difficult to determine what's going on here. We're looking at obvious cases here. In order to determine what's going on here, looking at a histogram and then comparing the mean and the median would be important. So now let's go ahead and talk about outliers in particular. Now the type of outliers that we're going to talk about are not ones that we just glance at and we think, gosh, that seems like an outlier. This is going to be the mathematical definition of an outlier, and we're going to go through and say how outliers are found. So that's how we're going to start looking at this as mathematically. In order to do this, the first thing we need to look at is called the interquartile range. It's abbreviated IQR, and basically the IQR is the upper quartile minus the lower quartile. Q3 minus Q1. And basically this gives me the spread of the middle 50% of the data, because I'm only looking at that middle box in a box plot. So this is the spread of the middle 50% of the data. And And it's probably a better estimate because it doesn't take into account the outliers in terms of the spread. So it's looking at the bulk of the data, and it says how is the bulk of the data spread out. Now an outlier is an individual that falls outside of the overall pattern. We've talked about that. But the problem is how far outside of the overall pattern does it need to be away from the data in order for it to be considered an outlier? Well, this is how we talk about outliers. We talk about any value that's less than, here's our less than sign, so any value that's less than our lower quartile, or Q1, minus 1.5 times IQR would be considered a low outlier. An upper outlier would be any value that's greater than our third quartile or our upper quartile plus 1.5 QR. So those are kind of the fences. And then when I go through and I calculate anything beyond that, then I call that an outlier, and I treat it differently on my box plot than I would any other point. So let's go ahead and look at our data set again, and in this particular case, when we calculate our outliers, we'll get some results that we're going to have to change how the box plot might look. Okay, so let's again look at this data set, our ordered data set where our sample is 25. We're going to go from the maximum value to the minimum, and we've already gone through and calculated the mean, or sorry, not the mean, but the median, Q3 and Q1. So in this particular case, Q2, which is the median, is 3.4. Now remember, 3.4 would be this bar right here then, and that looks well represented. Q3 would be represented by a bar as well. Q1, my lower quartile, is a bar too. Now this is the middle 50% of the data because Q3 minus Q1 would be 2/4 or 50%. So this is the middle 50% of the data. So the next thing I do is I calculate the inner quartile range, which is the upper third, or sorry, the upper quarter, Q3 minus Q1, and I get 2.15. Okay, so that's basically the range of the middle 50% of the data. Now I'm not going to talk about the maximum yet because a maximum and minimum points are the potential points for outliers. So what I'm going to do is I'm going to calculate kind of these fence points of where outliers could possibly be. So the first thing I'm going to do is I'm going to check for upper outliers. Now upper outliers will occur for any value greater than Q3 plus 1.5 times IQR. You have to grab out your calculators here because we're going to have to crunch some numbers. Q3 is 4.35. IQR we just calculated is 2.15. So when we crunch our numbers here, I'm going to take 1.5 times 2.15 and add it to 4.35, and you get 7.575. So anything that's greater in our data set than 7.575, I'm going to say is an outlier. Well, if you look at our data set, here we have one. Therefore, 7.9 is an outlier. Now, because it's an outlier, I don't represent it just with a dot or that bar like I used to and connect it. I represent it with an asterisk. So because it's an outlier, it gets an asterisk. Next thing we want to do is we want to look below it to see if there's any others. 5.6, that's not greater than 7.575, so we're okay there. Next thing we're going to do is look at lower outliers. So with lower outliers, I say anything less than Q1 minus 1.5 IQR. So we're subtracting here. Well, Q1 is 2.2. IQR in this particular case again was 2.15. And 2.2 minus 1.5 times 2.15 is, it's a negative value, negative 1.025. So if any data points are less than negative 1.025, they'll be in lower outlier. Well, you can see over here the smallest data point is 0.6. That's definitely not a negative number. It's not less than negative 1.025. So I'm good. This is not an outlier. So this is my minimum value. I can't reclaim it as an outlier, so there's no lower outliers. Now this was an outlier up here, so that's why it got an asterisk on my chart. And this right here then is my new max. So my new maximum is posted right here at 5.6. My minimum is 0.6, and then what I do is I extend the bars from my Q3 to my max, my Q1 to my min, and then this asterisk represents an outlier. And now it's pretty easy to talk about, well, without that outlier, this seems to be a fairly symmetric distribution. It really changes how we look at this. Now again, this is a box plot where I have gone through and calculated the outliers using the 1.5 IQR rule. And this is called a modified box plot in some software programs. So sometimes you won't just find box plot, but you'll have to ask for a modified box plot to use the 1.5 IQR rule. Minitab is pretty good about determining exactly the same outlier fences as we do in class. Quick side note, if you use software or your calculators to find the quartiles, the median, the box plots, sometimes they do them slightly differently, and they'll get slightly different answers because there's a different process to use. But everything that we've done here is how we'll do it for a test or a quiz. If you're using software and you get a slightly different answer, that's okay. Report the answer that you get. Just make sure that you don't have a mistake in how you enter data, and that's where the mistake is coming from instead of just a difference in how you calculate outliers. So again, sometimes technology will give you a slightly different answer because of the algorithms that they use to compute these values. So now that we know how to determine outliers, the next question is how do we deal with them? What do we do with them? Well, first of all, when you're dealing with outliers, you have to look for a couple of things. First of all, it could be something that was just recorded incorrectly. Maybe somebody put it into the computer wrong. Your book talks about Popeye the Sailor Man. If you haven't read it, go through and do that. It's kind of interesting. It talks about how we have the misconception that spinach is so full of iron and good for us because of basically a decimal error when recording data a long time ago. So again, human error in recording the information, human error in the experimentation or how the data was collected. And basically, we also have to take into account that you can get these extreme values in a data set. Not everybody is the same height. Sometimes you'll get somebody that's extraordinarily tall. Sometimes you'll get somebody that's extraordinarily short. So again, sometimes you will get a wild observation that is completely legitimate, and we need to keep it in our data set. We can't ignore it just because it's not convenient. So again, you can't just throw out outliers. Outliers are trying to show you something. You need to deal with them. And the first thing you should do is check to make sure it's not a mistake, and then keep it in the data set if it is not a mistake. Now, when we're working with data, we've learned a lot of different types of summary statistics I can look at. I can look at the mean, I can look at the mode, the median, for measures of central location or central tendency. I can talk about spread in terms of standard deviation and also in terms of quartiles. But the question is, with all these different measurements, which ones do I use when? So let's go ahead and look at choosing among the summary statistics. And we've already talked about a lot of these, but let's go ahead and kind of recap. The mean is not resistant to outliers or skew, so if we have a distribution that's very skewed, we shouldn't use it. But if we do have a distribution that's fairly symmetric and doesn't have a lot of outliers, a mean is a good value to use as well as the standard deviation. So how could we figure this out? Well, you could plot the data, look at a histogram, or you could also kind of plot the mean and use the standard deviation for error bars. So here's the mean. Here's the standard deviation. Here's one standard deviation. So this is one standard deviation above, and this is one standard deviation below. And we can see that there's not a lot of spread, and this will always be right in the middle because you're adding and subtracting the same value from the mean. So there's not a lot of spread here. It doesn't look like there's too much going on, but it's difficult to tell until we look at a box plot. So let's come over here and look at the box plot. If you have a skew distribution, it's usually a good idea to not only report the mean but also the median, because they will be such significantly different values. So we can see from this box plot that I have a fairly symmetrical distribution as well. Now this is the same data. So this is a box plot of the height of 30 women. This is the mean plus or minus the standard deviation for the same set of data. So we can see that the box plot shows symmetry. This will always show symmetry. So it doesn't provide a ton of information, but it does give us an idea about the spread. So if you have outliers or you have suspected outliers, a box plot, a histogram is a good thing to look at and see what we have going on before we determine whether to use the mean or the median. It's always a good idea to report both. It's not like it's difficult to calculate these values now that we have computers and calculators that do them so easily. Now let's use this information about skewness to determine something about a set of data. So the set of data that I want to look at is the phytopigment concentrations in deep sea sediments collected worldwide, and they're saying that they're showing a very strong right skew. So over here, as soon as I see the word right skew, I kind of think it looks something like this. Probably not exactly, but something like this. Now, which of these two values is the mean and which is the median? Well, if I have a right skew distribution, I know that the mean is somewhere over here in the direction of the outliers or the scale or the direction of the skew. And I know the median is somewhere over here by the bulk of the data. So whichever of these is a larger number will be my mean. So in this particular case, the larger number would be the 0.015, and that would be my mean value. So here's 0.015 for my mean, which would leave 0.009 for my median. Now, which would be a better summary statistics for these data? Well, we can see when we look at this that 0.015 is kind of over here and it's pulled in the direction of the skew. So I think the better measurement or the better summary to be using on this particular data set would be the median. But again, it's always smart just to report both of those. There's not a problem with reporting both of those. And again, they're easy enough to calculate using your calculators and computers. Last thing we're going to look at in Chapter 2 is to look at how we organize a statistical problem. When we organize a statistical problem, every book kind of has a different process that we go through, but they're all very similar and have type of the same ideas. They kind of follow the scientific method, kind of. And they usually look at a certain number of steps that follow through with a process that allows us to draw some particular sort of conclusions that are valid based on our process that we followed. So let's go ahead and look at the process that this particular book recommends. So again, when you're organizing how to work through a problem, the first thing that you should do is what you're trying to answer. What is the practical question? Am I trying to answer if a death rate is higher for one disease or another, if a medication is working, if a bone that I found is a certain age or from a certain species? Those are the types of practical questions that you can look at. The next thing we should do is try and figure out what process should I use to solve this. So you should design your experiment before you actually do the experiment to make sure that the results that you get will be able to be analyzed in order to draw valid conclusions. Next, you should solve is the step that they say, but make the graphs, carry out the calculations that are needed for the problem, find the summary statistics, talk about the skewness, talk about the symmetry, and try and do a basic overview and analyze the data. And of course, the last thing that you should do is you should always draw your conclusions in terms of a real-world setting. You shouldn't try and overcomplicate your conclusions, try and talk about them too statistically or too mathematically, but try and put them in layman's terms so when we look at the results we can kind of come to a direct conclusion. So this is Chapter 2. Make sure that you are also reading the text because there's a lot of information in there as well. So make sure you read, because that's going to be very important to get an overview of the entire chapter. And then also it's going to be very important that you learn to use your calculator. And again, if you cannot find your owner's manual or your user's manual, go online and type in the type of calculator you have, a TI-89 or a Casio or an HP, and they'll have a manual online that will take you through step by step on how to do these. If you get stuck and you're not sure what to do, bring your calculator up to my office hours, bring it to class, and we'll try and figure it out together. When you do bring it in, bring your owner's manual with you because I don't know how to use every calculator, and that will kind of give me an idea of where to get started as well. Also, you need to keep using Minitab. Minitab is very helpful, especially when we're talking about graphs and box plots and box and whisker plots. Stats Portal does a very nice job providing technology manuals for you for this chapter for Minitab as well. Excel doesn't do box plots natively. You can download macros to have Excel use box plots, as far as I know anyway. So make sure that you are looking at Minitab and just not Excel. If you have any questions, concerns, problems, please bring them to class. Email me or stop by my office during my office hours and I would be happy to help you out.